This video will be about how to create a bot project in C++. We're going to go over each portion of Iterative Robot, what it does, and how to use it to create a simple robot using Iterative Robot. So the first thing we're going to do is create an Iterative Robot project. We're going to go up to File, New, Other, and select Robot C++ Project. We're then going to select Iterative Robot and give it a name. And we'll be given a single template file called robot.cpp. And this file contains everything you need to get started for Iterative Robot. And if you get these kinds of errors, don't worry about it. If you just refresh the index, they should go away. Okay, so Iterative Robot is made up of essentially three main sections: the initialization section, the autonomous section, and the teleoperated section. And within both the autonomous and teleoperated sections, we have these functions called Init and Periodic. So what Iterative Robot will do is this function, robot init, will be run when the robot is first booted up, and that's the only time it will be run. So this is where you put stuff like initializing objects for your controllers and your sensors, any one-time initialization. This is where you would set up the chooser for choosing different autonomous routines on your smart dashboard, and stuff like that. Then in the autonomous and teleoperated sections, the init function is called once as soon as the robot enters autonomous mode. So not when it begins running autonomous mode, but when the mode is switched to autonomous. And similarly for teleop init is run exactly once when teleop is entered. And if a robot enters teleop init is run. Then if it leaves teleop to go to autonomous and comes back to teleop init will be run again. And then the autonomous periodic and teleop periodic functions are run continuously during the entire duration of the robot being in either autonomous or teleop mode. And test periodic is similarly a function that will be run constantly as long as the robot is in test mode. So with that out of the way, we can start programming our first robot in Iterative Robot. So this is going to be a simple robot. It's just going to have two motors in the drivetrain, two encoders hooked up to those motors, a single LED digital output, and a joystick controlling everything. So the first thing we're going to have to do is set up the objects to control these sensors and controllers. So we're going to do that by going down and creating some new members of the robot class. So actually, first we have to include the headers for these classes. So we'll need to include the robot drive header, the encoder header, the digital output header, and the joystick header. Now with that out of the way, we're going to start setting up our robot. So you could use objects allocated inline in this class, so you could just do something like frc robot drive drive. That could work. I chose not to because one, in case you want to start passing this around to other things, or maybe move your declarations for these objects into a separate file, you don't want to be passing these objects around. And you actually can, because these have deleted copy and copy assignment constructors. So I'm going to heap allocate them, but this is really this is a design choice you should make for your actual robot. So, and as I hope we all know, modern C++, we should never have owning raw pointers. So we're going to use a smart pointer. We're going to use a unique pointer in this case. So we're going to have a unique pointer to a robot drive object. I'm going to call that drive. Similarly, we're going to have one for the left encoder and one for the right encoder. We're going to have an object for the LED light. So and finally, we're going to have one for our joystick. There we go. We'll have one for our joystick. Okay. We're also going to declare some constants for the ports that these are going to be plugged into. So on your actual robot, you'll have to figure out the ports that these are plugged into and specify them. I'm going to make up some numbers for this, just so it compiles and it works. So I'm going to say the left motor is in port 0. The right motor is in port 1. The left encoder, so encoders typically take up 2 digital input ports, an A and a B. So I'll say the A port is in digital input 0, B is in 1. Similarly for the right encoder, A is in 2, and B is in 3. Then we're going to need a digital output port for the light, so we'll say that's 0. And finally we need a USB port number for the joystick, so we'll call that 0 as well. Alright, so now we have everything we need to set up our actuators and our sensors. So what we're going to do is we're going to scroll up to robot init, and this is typically where you would initialize these types of objects because they only happen once when the robot is first booted up and never again. So we're just going to do pretty standard setting it up. Drive equals standard make unique. And we're using make unique to avoid that one extra allocation because, you know, why not? So robot drive takes in the ports of the left and right motors. So we'll pass it in like this. Then for the left and right encoders, they take in their A and their B in that order. And if you switch up the A and B ports for an encoder, nothing really bad happens. You'll just get a reversed sign on your reading. So if you can just account for that in software, it's not a big deal. Okay, then we're going to set up our LED light. So and finally our joystick. That's important, Joy. Okay, so that's technically all you need to get set up, but I like to include one more thing because you never really want to specify all your encoder readings in ticks, whatever the native tick measurements are for the encoder. You want something nice like feet or meters. So the encoder class is a really handy method that lets you set the number of ticks for a given distance, which you would determine through like empirical measurement or looking at your gear ratios, and also your wheel circumference. And that way you can query the encoder for a distance measurement, which is usually more useful. So to do that, we're going to set up a constant to indicate, let's say, feet per pulse of the encoder. And obviously, I don't have a real encoder or a real robot, so I'm going to make a bogus number like 0.005, because that looks good. And then all we do is, under here, we can say, for the left encoder, we set distance per pulse, and we set it to feet per pulse. And we do something similar for the right encoder. Okay, so this is going to make our lives easier, as you'll see in a bit. And this is pretty much all we need to set up our sensors and our actuators. So now we're going to move on to setting up our autonomous routines. It's going to be really simple. We're going to have two options in the smart dashboard, one for a do-nothing autonomous and one for a move forward 3 feet autonomous. So first we're going to set up some auto names to put on the smart dashboard. So if we scroll down here, the template actually already gives us a code for setting up 2 different autos, so we're just going to customize that to our needs. So we're going to call the default auto do nothing, and we're going to make a drive auto, which is drive forward 3 feet. So we're going to have to update these names here. And here as well. So here's where we get really into the guts of iterative robot. So we're going to be messing with both the autonomous init and autonomous periodic functions. So what we want to do is, depending on what's selected, we want to both perform that action, and we'll say that if we're performing the drive forward auto, we also want the LED light to come on and to indicate that we're going to be moving. So what we're going to do is, first in autonomous init, we're going to turn on that light whenever we're about to drive forward. So we see here they've already set up code to get the selected autonomous from the chooser, and there's options here for both Smart Dashboard, which is the first one, and the Lab View Dashboard, which is the one that's commented out. So in this case here, where we have the drive forward auto, we're simply going to set the light to be on, and otherwise, just in case the light was on before for some reason, we'll set it off. So now, depending on whether we're driving or not, the light will be either on or off for the entire autonomous. And so what we'll do then is, then we'll move to autonomous periodic, and here we put the actual code that performs the autonomous routine. So the default autonomous will do nothing, so we can leave this empty. But here, what we'll do is we'll say that, actually, we should probably do something else in autonomous init. We should reset the encoder. In case the encoder's already been spun up for whatever reason, we want to make sure we're not getting a reading from before autonomous started. So we're going to do, we're going to reset both encoders. So, okay, so now what we're going to do is, as long as the value of, so as long as both encoders, or let's say one of the encoders has not exceeded, so let's say until one of the encoders exceeds 3 feet, we're going to move forward straight at half speed. So the way we do this is we'll say if, so we'll get the distance from the left encoder. So if that's less than 3, and the distance from the right encoder is less than 3, so this means that we haven't hit our 3-foot mark yet. So we will drive forward with a speed of 0.5 and a curve of 0. And then if we have hit that, right, we're going to make sure to stop the robot. So notice here how I'm using an if-else and not a while loop. The reason is that this autonomous periodic function itself will be called in a loop. So we want to minimize the amount of time that we spend spinning in a loop inside of autonomous periodic. We want to let the loop that controls this handle that. So all we do is manage the conditional control flow here to say if we haven't hit our 3-foot mark, move at half speed. Otherwise, we stop. So that's our autonomous. We're done. So this will do exactly what we want. If we have the drive forward autonomous selected in Smart Dashboard, it will switch on the LED light and drive forward until it hits 3 feet. Otherwise, it will set the light off and do nothing. Now, note that if you actually want to do this autonomous, this is not the best way to do it in an actual competition. This type of bang-bang control, as it's called, is bad. It's rather imprecise, and you're prone to overshoot that distance. So I don't recommend it unless you really don't need the precision. But for the purposes of this demonstration, it does what it needs to. This is how you would do something like this in Iterative Robot. So with autonomous out of the way, we're going to move on to Teleop. So in Teleop, we want to make sure we clean up any changes that happen from autonomous or previous runs. So the motors won't be running. The WPI lib systems will see to that, and the safety system. So the motors won't just start running haywire, but we do want to make sure that our lights are off and all that kind of stuff. So when we enter Teleop mode, we're going to want to make sure that we set the light off, and let's reset the encoders as well. Not for any particular reason, just for the sake of demonstration, to show that we can do this. And then inside Teleoperated Periodic, this is where the main portion is going to happen. This is where the operator control code is going to be. So what we're going to do is we're going to get some inputs from the joystick, and based on that, we're going to move the robot. So the control scheme we're going to use is that by default, we're going to let the driver use tank drive to control the robot, but they can hold down a button for arcade drive, and additionally hold down a different button to trigger the light. So what we're going to do is we're going to say if joy, and the way to get button input is get raw button, and you're going to have to look up your specific joystick to find out what inputs are mapped to which ports, but I'm going to pick an arbitrary port here. Let's say port 1 is our arcade drive port. So if that button is pressed, we're going to drive the drivetrain using arcade drive. So we'll say drive arrow arcade drive, and we will, for the forward backward movement parameter, we will say we'll get from the joystick raw axis 0. Again, for your specific joystick, you're going to have to look up what axis is mapped to what input, but I'm going to arbitrarily pick axis 0 here, and our curve parameter is going to be, or I guess our rotation parameter for arcade drive is going to be on axis 1, let's say. So if raw button 1 is pressed, then we arcade drive. Otherwise, we're going to tank drive. And let's say that we're going to use axes 0 and 2 for this one. I believe on the Logitech controllers, raw button 1 is like A. I don't know what those axes are, but you'll have to figure it out for your own controller through either just testing. I believe you can even do it through the driver station, or you can look up a manual. So we also want to control the light. So if, say, we wanted to turn on the light when arcade drive is being triggered, but not during tank drive, we could do something like this to true during arcade drive and false during tank drive. That's no fun. We want to give our driver the ability to create a real light show, so we're going to bind it to a separate button. So we're going to say light arrow set, and we're going to set it to the input on button 2. So joy arrow get raw button 2. So this way, whatever is being pressed by the driver on button 2 will be sent directly to the light. So again, like autonomous, notice how we have no loops here. We don't want to be spinning inside this function because that will likely interrupt the scheduler from doing other things. So we just condition on the current state of the robot and do what we need to do, and then this will be called again in a loop for, however many milliseconds later. So that's really it for a basic robot implementation, iterative robot. This is all. It's pretty straightforward. It's good for building simple robot configurations. It's also good if you want a lot of control over how your code is structured. This is a great starting point for you to build it off of. So yeah, that's it for iterative robot. To go over the main points again, you put one-time initialization stuff in robot init, like initializing objects for your drivetrain, your encoders, your joysticks. In your autonomous init and teleop init, you run code when you first enter those modes. In autonomous periodic, teleop periodic, test periodic, those functions are run in a loop in those modes. So yeah, that's all for iterative robot. Hope it helped.